Hey folks, day 2 of our unit on antiderivatives and integration. Today we're going to be looking at finding solutions to differential equations, but before we do that, we are going to do a little bit of review from what we did in the last lesson, just basic antiderivatives using the power rule for antidifferentiation. So we're going to look at 6 functions here, and for each we're going to write the problem using integral notation, and then we're going to find the indefinite integral of the given function. So remember, the basic idea is that when we integrate a function, we're going to add 1 to the exponent and then divide by that new exponent. So to write this problem, we're going to say that we want to integrate this function 3x squared with respect to the x variable. That's basically what that dx is telling us right there. And I'm going to just write the 3x to start, and then I'm going to add 1 to the power. So instead of a power of 2, it's a power of 3. And I'm going to divide by that new power and add my constant of integration, which I do any single time I integrate. Now that I have it written down, now I'll simplify it. 3 over 3 is 1, and so I get the function x cubed plus c is my big F of x function, the antiderivative of 3x squared. So that's the basic idea. We're going to look at a few problems that get slightly more complicated than that, but they're all going to use that same idea. Add 1 to the exponent and then divide by the new exponent. So now we're looking at the integral of 2x to the 7th minus 4x to the 5th plus 13. We are integrating that with respect to x. Notice how I put it in parentheses because it's more than just one term. And now let's integrate. So we will add 1 to each exponent. So 2x to the 7th becomes 2x to the 8th divided by 8 minus 4x to the 5th becomes 4x to the 6th divided by 6 plus 13. If we do not have any x term there, if we're integrating a constant term, we get an x, and we could divide by 1 since the exponent there is now 1, but it doesn't really do anything. And then we have our plus c constant of integration. So let's simplify this down to get our big G of x function, which is going to be 2 over 8 is 1/4. So we're going to get 1/4 x to the 8 minus 4 over 6 is 2/3 x to the 6th plus 13x plus c is the indefinite integral of that little g of x function that we started with. Okay, remember what we have to do here. Before we can integrate this, we need to rewrite that x cubed that's currently in the denominator. We need to write that up top using a negative exponent. So we're going to be finding the integral of 4x to the negative third right there. I can't write. 4x to the negative third with respect to x. We will be adding 1 to our exponent, so instead of being a negative 3, it is now a negative 2, and we divide by that new power, dividing by negative 2, add our constant of integration, and now let's simplify. 4 over negative 2 gives us a negative 2, x to the negative second, plus c, which we could choose to write as negative 2 over x squared, plus c if we wanted to, and that would be our big h of x function right there. Okay, let's do another one. I of x is negative 5 times the 4th root of x, which is the same as negative 5 times x to the power of 1/4. That's what we will be integrating. Negative 5 x to the 1/4 with respect to x. When we integrate that, we're going to have our negative 5. We are going to add 1 to our exponent. 1/4 plus 1 gives us 5/4 plus our constant of integration c, and we added 1 to our exponent to get 5/4, so we need to divide by that 5/4. Well, remember that dividing by a fraction, dividing by 5/4 is the same as multiplying by the reciprocal of that fraction. So really what we have is negative 5. Instead of divided by 5/4, we can say times times the reciprocal of 5/4, which is 4 over 5. So I have negative 5 times 4 over 5 times x to the 5/4 plus c. Simplify that, well, my 5's cancel, and I'm left with negative 4 times x to the power of 5/4 plus c is my function. Okay, the most complicated one we're going to look at today, j of x, this big, messy, ugly fraction. Now remember, we cannot take the antiderivative of a fraction, or rather we don't know how to, and so what we need to do is we need to split this up into 1, 2, 3, 4 individual terms first. So I'm going to say 4x to the 4th over 3x squared minus 2x to the 2/3 over 3x squared plus 5x to the 7th over 3x squared plus 6x squared over 3x squared. All I did was write the denominator under each term individually, because now I can simplify. 4/3 x to the 4th over x squared becomes x squared, because you subtract the power of the denominator from the power of the numerator, minus 2/3 will stay there. X to the 2/3 over x squared, what does that become? Well, let's take 2/3 and let's subtract 2 from it, because the power in the denominator is 2, which is the same as 6/3, which gives me negative 4/3. So I get x to the negative 4/3 right there, plus 5 over 3, x to the 7th over x squared becomes x to the 5th, plus my x squareds cancel, and I'm left with 6 over 3, which is 2. So this is my function j of x, and now I want to integrate this whole thing. So I'm going to be lazy real quick and throw my integrate symbol right there, put my dx back there. That's what we're trying to find. So let's do it. We have 4/3 times x squared is going to become x cubed, and we're going to be dividing by 3, which is the same as multiplying by 1 over 3, minus 2/3 times x to the power of negative 4/3. I need to add 1 to negative 4/3, so I get negative 1/3. I need to divide by negative 1/3, which is multiplying by 3 over negative 1. And then plus 5/3, x to the 5th becomes x to the 6th, and I need to divide by 6, which is multiplying by 1 over 6, plus 2 gets an x, and we have our plus c. And now we can simplify things. 4/3 times 1/3 gives you 4/9 x cubed minus 2/3 times 3. Those 3's cancel. Notice my negatives cancel, so I'm left with 2x to the 1/3, negative 1/3, sorry, plus 5/3 times 6 gives me 5 over 18 times x to the 6th plus 2x plus c. This is my big j of x function. Kind of messy, but totally doable when you take it piece by piece. And then the last one here, L of x, same idea as j of x. We don't know how to integrate a product here. And so before we do that, we need to simplify it. So we need to distribute in x times x cubed. With that 2 there is giving me 2x to the 4th minus 27 times 2. I'm actually going to leave as 2 times 27 for now. You'll see why in a minute. You could also just multiply it and get 54. Don't care, it doesn't make a difference, but I do have that x there. Now that's what I'm integrating. I'm integrating this function, 2x to the 4th minus 2 times 27x, with respect to my variable x. And so 2x becomes 2x to the 5th right there, divided by 5, minus I have my 2 times my 27, my x becomes squared, and then I need to divide by that 2, and then my plus c. Do you see why I didn't multiply that 2 in? Totally could have, but now I can see those 2's cancel, and so I get 2 over 5 x to the 5th minus 27x squared plus c is my function. Sorry, not j of x. That was the last one. That's my function L of x right there. And we just did a bunch of integration. Basic idea, add 1 to your exponent, divide by that new exponent. So, plan for the day, review indefinite integration. That's what we just did. Now we're going to look at solving differential equations for specific solutions, and then we're going to look at some population growth models. So very briefly, just reviewing our notation, we have our integral symbol right there. It's telling you to integrate the function f of x, which is our integrand. We are integrating with respect to the x variable. That's what that dx is telling us. And we will end up with some antiderivative, big F of x, plus c, the constant of integration. So, we have always had that plus c up to this point, but now we're going to look at solving differential equations for specific solutions, which means I have a derivative here, dy over dx equals 12x squared minus 4x. I know it's a derivative because of that notation, dy over dx, and I am given a point, 1 comma negative 3, on the graph of y. So real quick, think about what we're doing. We're integrating dy over dx with respect to x, which means I will get my function y plus some constant of integration, which I will then need to figure out. So I'm going to integrate this function, 12x squared minus 4x dx right there. So I'm going to get 12x cubed over 3 minus 4x squared over 2 plus c. And let's simplify that. 12 over 3 is 4x cubed minus 4 over 2 is 2x squared plus c. That is my function y. And what do I know about my function y? I know that this graph has this point, 1 comma negative 3. And so I'm going to plug that point in to solve for c. So I'm going to get negative 3 equals 4 times 1 cubed minus 2 times 1 squared plus c, and I can solve for c. So negative 3 equals 4 minus 2 plus c, and I can solve that to get that c equals negative 5, which means I've found my constant of integration, which means rather than writing this equation generally with that c, I can substitute that c value in to figure out the specific solution to this differential equation. The specific solution, all we did differently was after we integrated, we substituted that point in and we solved for c, and then we wrote our equation. That is what we're doing when we're solving a differential equation for a specific solution. So let's do another one real quick. We're given a derivative, f prime of x is equal to negative 1 over x squared. We're given a point on the function f, the antiderivative of f prime right there, and we want to solve it by finding the specific solution. So we need to integrate and then find the c value. So we're integrating the function negative 1 over x squared, which I am going to write as a negative x to the negative second. We're integrating with respect to x, so let's use our power rule. We have our negative out front still. X to the negative second becomes x to the negative first when we add 1, but we need to divide by that new power, negative 1, plus our constant of integration there. And so notice what cancels. I have a negative 1 over a negative 1, so I get x to the negative first, which is just 1 over x. And then I have my plus c right there. That is my function f of x. But now I need to plug in the point I know. F of 1 equals 7. That's telling you that x is 1 and y is 7. Remember how to read function notation. So I'm going to plug in and say 1 over 1 plus c equals 7. And I'm going to get c equals 6. And so I can write my function f of x as 1 over x plus 6. And that is my specific solution. So let's think about what this c value represents in the context of these last two problems. In this problem right here, that 6 is representing the horizontal asymptote of this function 1 over x. Remember what you know about the mother function, 1 over x. It is a rational function. It has an asymptote at x equals 0. So compare that to the last problem where we found c was negative 5. That was corresponding to the y-intercept right there. So that's useful information. That will come in handy in a moment. Let's do one more and then we'll look at a specific application of this. So we have a function f of x here. We want to find the antiderivative, big F of x, and so we will integrate 3 over 2 x to the 1/2 plus 2 with respect to x, and so we're going to add 1 to the exponent, x to the 1/2 will become x to the 3/2, add 1 there, and then divide by 3/2, which is the same as multiplying by the reciprocal 2 over 3. Add 2, we need to add that x there, and then we have our plus c. This will be our big f of x function. And now we can simplify 2's, 3's, so we're left with x to the 3/2 plus 2x plus c as that big f of x function. But we know a point on big f of x, we know that the x value is 4 and the y value is 9. So we get 4 to the 3/2 plus 2 times 4 plus c equals 9. So 4 to the 3/2, that's telling you to cube 4 and then take the square root of 4. Take the square root of your answer, or it's telling you to take the square root of 4 and then cube that answer. So I'm going to take the square root first because that's easier. Square root of 4 is 2, and then 2 cubed is 8. So I get 8 plus 2 times 4 is 8 plus c equals 9. So let's figure out what c is. Subtract 8 from 9, you get 1, and then subtract 8 from 1, you get -7. So c is -7, and we can write our equation, big F of x equals x to the 3/2 plus 2x minus 7. And we are done. So we just solved differential equations for specific solutions. And now I want you to solve the twice differentiable function. I give you a second derivative, I give you a point on the first derivative, and I give you a point on the original function. So let's remember how this works real quick. If I have f of x and I take the derivative of f, I get f prime of x. If I have the first derivative and I take the derivative of that, well, I'm going to get f double prime of x, the second derivative. Well, integration takes us the other way. If I have f double prime and I integrate it, I'm going to get f prime. If I have f prime and I integrate it, I'm going to get f of x, the original function. And I could go above that if I wanted to. I could continue to integrate as long as I wanted to. So we are now essentially doing the same exact thing we just did, except now we need to do it twice. So I am going to integrate my function f double prime of x to get my function f prime of x. So I'm just integrating the function 2 with respect to x, which means I will get 2x plus c, and this is going to be my f prime of x function. And I know a point on f prime, so I need to plug that point in. So my x value is 2, so I'm going to get 2 times 2 plus c equals 5, the y value there. And so c equals 1, and so I know that f prime of x equals 2x plus 1. Now I need to integrate f prime to get f of x. So I'm going to be integrating the function 2x plus 1 with respect to x. And so when I do that, I'm going to get x squared plus x plus c, and that will be my f of x function. And again, I need to solve for c. So I need to plug in my x value of 2, and I need to plug in my y value of 10, and I need to solve for c. 2 squared is 4, plus 2 plus c equals 10, so c has to equal 4, and so I know that f of x equals x squared plus x plus 4, and I have solved this twice differentiable function for the specific solution x squared plus x plus 4 using those initial conditions. Let's do a couple more real quick. Same exact idea. We're integrating this x squared function with respect to x, and so I will get x cubed over 3 plus c, and that will be f prime of x, and I know a point on f prime of x. I know that the x value is 0 when the y value is 6, and so I get 0 cubed over 3 plus c equals 6. And like, what happens? 0 cubed over 3 is 0, so I get c equals 6. And so I get f prime of x equals x cubed over 3 plus 6. And now I want to integrate that function, and so I need to integrate x cubed over 3 plus 6 with respect to x. Doing so, I will get x cubed becomes x to the fourth, which I need to divide by 1/3, and then I'm dividing by 4 is going to give me that 1/12 right there, plus 6x plus c, and now I need to plug in my point and solve for c, because this is now my f of x function. So, do so, again, the x value is 0, so I get 0 to the fourth over 12 plus 6 times 0 plus c equals 3. And look, that term's gone and that term's gone, so again, you're left with c equals 3. And so then f of x has to equal x to the fourth over 12 plus 6x plus 3. And what I want you to notice is that when your x value is 0, whatever the corresponding y value is, that is your c value. So that's pretty useful information to know and will help us in the future. So let's look at two applications of this idea real quick of solving differential equations. So here's a problem. We are a tree farmer. We sell pine trees after 8 years of growth. During that time, the rate of growth is modeled by the function dh over dt equals 1.7t plus 4, where t is the time in years and h is the height in centimeters. We're told that the seedlings were 10 centimeters tall when planted, and we want to know how tall are the trees when they're sold, and what is the height function that models this tree growth. So you should recognize that we are dealing with a derivative here, looking at that notation, dh over dt. If we integrate dh over dt with respect to t, we will get a height function in terms of t, h of t. That's what we're looking for. So what do we know? Well, we have that function and we should integrate it. So let's integrate our function 1.7t plus 4. And so when we integrate that, we get 1.7t squared, 1.7t squared over 2 plus 4t, not 4x, 4t. Our variable of integration is t, not x. And then we have our plus c. And this is our height function, h of t. Well, we can simplify this a little bit. It doesn't really make a difference, but 1.7 over 2 should give us 0.85 t squared plus 4t plus c equals our height function, h of t. Now, how are we going to find that c value? Well, we're told that the seedlings were 10 centimeters tall when planted. We're modeling the growth of them after they've been planted, and so that's telling us the initial point when time was 0, the height was 10, which from that previous problem we discovered that is telling us essentially that c is 10. So we have our height function, h of t equals 0.85 t squared plus 4t plus 10. And now if we want to know how tall they are when they're sold after 8 years, so just plug in that value, 8 for t, we'll get 0.85 times 8 squared plus 4 times 8 plus 10. And when you simplify all of that, you should find that the height after 8 years is 96.4 centimeters. Which is maybe a little unrealistic, but, you know, the math checks out, and that's all I'm interested in. So, okay, using differential equations to solve a problem. Let's look at one more, and then we'll call it quits. Population P of bacteria grows according to the model dp over dt, so again, recognize that as a derivative, a growth function. It equals some constant k times the cube root of t, where k is an unknown constant, and t is the number of days of growth. And then we know two things. We know the initial size of the population was 200, which is telling us a point, 0, 200, which is telling us that c is 200. And we know that the population after 2 days has grown to 450, so we know that we have the point 2, 450 on our population equation. So we need to integrate this. So we're integrating k times t to the 1/3, t to the 1/3 right there with respect to time. And so when we do that, what do? Well, we add 1 to our exponent on the variable we're integrating. So 1/3 becomes 4/3. We then need to divide by that exponent. So instead of dividing by 4/3, I will multiply by 3/4. And then I still have my k out front, just hanging out. But I do now have my constant of integration plus c. And so I have my population model. P of t equals k times 3/4 t to the 4/3 plus c, but I know that c is 200. So I have this model right here, and I want to solve for that constant k. I want to know what is that coefficient right there. What does it become? And to figure that out, I need to plug in my second point, 2 comma 450. So I know I have the equation 450 equals k times 3/4 times 2 to the 4/3 plus 200. And I need to solve this for k. So what am I going to do? Well, I'm going to take 450. My pen is not working very well. I'm going to take 450. Notice I have that 3/4 on the other side, so I'm going to multiply by 4/3 to undo that. And then I have, oh, sorry, I'm lying, doing bad things. If I'm solving this for k, first thing I should do is subtract that 200 over. So I'm going to get 450 minus 200. It's going to be my first thing. And then I'm going to multiply that by the 4/3. And then I'm going to divide all of that by that next coefficient on k, 2 to the power of 4/3. I don't care if you do this in pieces and get actual numbers, but you should be able to work backwards and get k by itself. To find that k is roughly 132.283. And so the question is, what's the size of the population after 10 days? And now we have that k value, so we need to plug that into our equation. So we know that the population model with respect to time will be that k value, 132.283 times 3/4 times t to the power of 4/3 plus 200. I now know my population equation, so I just need to plug in to solve for p of 10. And you should get 2,337.470. Now in terms of entering that in, after finding k, I would have just hit times. It would bring up answer times using that k value. Then I would put parentheses and do 3 divided by 4, close the parentheses. Then I would hit multiply. I would type 10 for the time. If you're on an older calculator, make sure you put your 4/3 exponent in parentheses, close them off, and then add 200. You should get this 2,337.47.